All right, thank you. This is Craig Hartman. We are doing number 3 of our Getting the Most from Your Electric Motor series. As we mentioned before, this is all based on an ESA booklet. ESA is the trade organization that most motor repair shops belong to, kind of a third party. And as if you've been with us the last couple of presentations, you'll notice this is just pretty straight technical stuff. There isn't a lot of marketing in this, and I think it's very helpful. It's a good book to have. If you would like a printed version of the booklet, Tyler will be happy to send you one. And I personally think that's a good idea. I mean, I know everything's done with electronically these days, but I kind of like to have this printed version that I can just pull out and flip through the pages. All right, this is where we started. We started with how does a motor work? Got into single phase motors and how they work. And if you weren't with us on the first presentation, then this is some of the stuff that will be in that presentation that is available. And then we got into elevation, quite a bit on motor temperature rise, how to tell with or without sensors whether your motor is over temperature. We talked about different types of motor enclosures. Talked about mounting, alignment, vibrations, the different types of bearings, and then spent a fair amount of time talking about how to lubricate. We mentioned this is a good lubrication job, but you certainly wouldn't want your motor to run this way. It would be like trying to run in a swimming pool. And so that's great to have that amount of grease in there. Remember, the grease is not the thing that lubricates the bearing. The oil in the grease lubricates the bearing. The grease is just there to hold the oil in. And so you need to leave your drain plug out, run that motor for about 30 minutes to allow this to pump that excess grease out. Otherwise, your bearing will run hot. Just one of the many problems you can get into with regreasing. And as you know, the number one reason for motor failure is bad bearings, and the number one reason for bearing failure is improper lubrication. Could be too much grease, too little grease, the wrong kind of grease, but mostly it's just greasing in the wrong way. So let's talk about right here. This is where we ended. How often do I regrease? Now, not only do you need to worry about the bearing being too hot, but you do need to worry about, the motor being too hot, but the bearings as well. So a simple rule for troubleshooting bearings, this is from SKF Bearings, a reputable manufacturer of bearings. No more than 180 degrees Fahrenheit on the housing. So as you know, infrared cameras are pretty inexpensive these days. And by just looking at the housing, this is the bearing housing, then you shouldn't be more than 180 degrees on there. If the thing gets too hot, your grease can liquefy and run out, and then you end up with no real lubrication, and you're looking at a failure of the bearing. This is a better procedure for hot bearings. Again, this is from SKF Bearings. This is official stuff, word for word from them. Check the housing surface temperature. It might be okay, even though most people find anything over 130 degrees too hot to touch. Slowly add the proper amount of fresh grease to the application. If it's a motor or other machine with a grease relief, open the relief and allow excess grease to escape. Then monitor the temperature, make sure it doesn't run away. You'll often get a temperature spike after adding grease. That's because that bearing's packed with grease and it has to pump out the excess grease. That might take about 30 minutes to stabilize. If the temperature continues to increase, then you have a runaway thermal problem and you're going to have to investigate. You notice here in the top graph, this is not something you would do, but they lubricated every 24 hours. And so they lubricated, then 24 hours, they lubricated again, another 24 hours, lubricated again, and 72 lubricated again. This is not a proper way to lubricate, but it's good for a test. And you can see how when they put the lubrication in, the temperature goes up because that grease, that bearing is packed full of grease, and then it comes back down to its normal operating temperature. So that's kind of a pattern that you should see when you lubricate your motor. Grease composition. All greases are comprised of three things: a base oil, a thickener, and an additive. All greases deteriorate. They oxidize, the oxygen gets in there and oxidizes the grease, causes it to age, we'll say, or to oxidize. Oil bleeding, you always get some oil bleeding, but too much oil coming out of that grease will then decrease the ability to lubricate that bearing, because oil, again, is the thing that actually lubricates the bearing. Mechanical working, as the grease moves around, as you work it and work it and work it, that causes grease to age. And then, of course, there's evaporation. So all greases are going to degrade over time. And that's why I love the idea of a sealed bearing and never having to grease it. It's a great idea. Unfortunately, grease just doesn't last forever. And so if you don't grease it, typically the manufacturers tell us you should plan on a 3-year life. That, of course, is assuming that the motor is running 24/7. So if you want your motor to run years and years and years, then you'll need to get a motor that is regreasable. These are some of the additives that you get: antioxidants, rust inhibitors, anti-foamers, additives for a stronger oil film. Here's some of the grease types. Now, people use all sorts of greases. However, and let me move over here. Wanted to get past the viscosity. Here you go. This is your proper bearing lubrication and care, and it shows all the different types of greases. I like this statement. I found this in a paper on polyurea grease up on the top. It says, polyureas are like women. There are many, and they're all beautiful. So polyurea has become the go-to grease. But if you get a new motor, pretty much that's what you're going to get, assuming it's a greasable motor and not an oil motor. It has grease rather than an oil bath. But this is a table that is in your booklet, and it shows all the different types of greases and which ones are compatible with one another. And you can see a C would be compatible, an I would be incompatible, and a B would be borderline. So if you go down here to a polyurea conventional, you'll notice it's pretty much only compatible with itself. Now, there are polyurea shear stable compounds that they advertise as being compatible with other greases. But my advice is simply look at the grease and make sure that it is compatible with whatever is in there already. I know that may be difficult because you may not know what's in there already, but polyurea tends to be the standard these days. On the bottom, you can see a picture of some Chevron grease. And as I said, polyureas are the standard grease due to their high temperature performance, inherent antioxidant properties, and their high shear stability. Also, polyureas, because they degrade slower than the other greases, are really the best grease for a sealed bearing or a sealed for life bearing. And they were originally developed in Japan. Now, here's oil lubrication bearings. We don't have time to get too much into oil, but this would be, say, a vertical motor with an oil bath, which you don't grease, you fill it full of oil. Oil vendors use many different additives, some of which are not compatible. So again, you need to stick with the same oil. And you can have similar properties with oil as you do with grease. So try to go with the manufacturer's recommendation. One of the stories, you can change oils. I remember when I was the director of engineering for Geneva Steel, and we had actually 3 motors that we had bought, used, and put them in. They were vertical motors, and they had an oil bath, and we just couldn't get that oil viscosity down. And finally, we drained the oil and put in Royal Purple, which of course is a 100% synthetic oil. And I was quite frankly amazed that oil temperature came down much faster than, or much more than I expected that it would. So it's very important with oil lubricated bearings that you use oil that's rated for the temperature that you're going to be running. This table is in your booklet, and it talks about how to select oil and for the proper temperatures and so on. So I'm going to refer you to that due to time today. Here's your isoviscosities and what temperatures those isoviscosities are rated. And where is this? It's in the booklet that we've been talking about. Sleeve bearings. I love sleeve bearings. Sleeve bearings just tend to last forever. They'll outlive you. As you know, sleeve bearings have a little brass ring on there, and they dip into an oil bath and lubricate that sleeve bearing. Again, it is temperatures very important, and this will give you some information on how to properly do sleeve bearings. Where can you find that? In the booklet. Here's some pictures. This is a picture of a bearing that we've taken a picture of, and people who rewind motors, repair motors, refurbish motors tend to be really, really good at understanding bearing problems, and most of them have been through bearing training classes with bearing suppliers and are certified with those bearing suppliers. All of our people are certified with 2 different bearing suppliers, and they get pretty good at bearings because they see them all the time. So here is a bearing. This is the outer race, and you can see that is discolored. This would indicate improper lubrication or lubrication method, or possibly an inappropriate type of lubricant. Just a second, there we go. Sorry, my computer wasn't responding very well. Here's one. Take a look, and you can see that these are the roller ends, and you can see how they're scuffed around there. So that scuffing also is an indication of either improper lubrication method or an inappropriate lubricant. And we talk quite a bit about the proper way to lubricate. Many people are not lubricating properly, and if they did that, they would see much better reliability out of their motor. So this is one of the things that can happen. Now, this is a pretty bad situation in which you have retainer wear. Those are the rollings, and the retainer, did I say rollings? Rollers, and the retainer has actually worn sufficiently that some of those have fallen out. So this is, again, improper lubrication method or an improper lubricant. Now we want to talk about variable frequency drives and motors. We've been telling you we are going to get into this, and now's the time. So I want to look at 2 things. This is a nameplate from an Emerson US Motors, and I have a picture of it because I'm proud of Emerson. I think they did a great job on the nameplate here. Most motors are not going to have all this information, but you'll notice that the top part of this nameplate has the regular motor information, and it has the data for running the motor across the line, and the bottom gives you specific data for the motor running on an inverter or a variable frequency drive. Now let's notice first over here on the upper left of the inverter duty portion of the nameplate, it says NEMA MG1 Part 31. That's the first thing we want to look at because that has to do with the insulation, and we will cover that in a moment. Most motor nameplates don't have that, and you actually have to go to the data sheet or maybe even call the manufacturer to find that out. But when we talk about what is an inverter duty rated motor, that is the first thing you want to look at, and we'll talk about that momentarily. Now, next is service factor. Notice that when we're running this thing across the line, this is a 1.15 service factor motor, and when we're running it on an inverter, it's only a 1.0 service factor motor. So this is the standard for variable frequency drives. If you're going to run a motor on a variable frequency drive, you must always specify a service factor motor, either 1.15, which is the most common, or a lot of motors are 1.25. Our Galt motors, a lot of those are 1.25. But you need at least 1.15 service factor, and that indicates that the motor across the line can actually run 15% over its rating without overheating. But when you put it on a drive, you cannot use that service factor. It becomes a 1.0 service factor. Why is that? The reason is that if you're putting it on a drive, you pretty much know that you're not going to be running at full speed. Now, that may or may not be 100% true, but the fact is most drives are going to run somewhat slower. As they run slower, the cooling fan on the motor is going to run slower, therefore you're going to get less cooling. And so we use up the service factor to compensate for the fact that as we slow down, we get less cooling. And any motor that is VFD rated will have a spec that says you can run this speed range on a variable torque or this speed range on a constant torque. And typically, if you have a good cast iron TEFC motor with 1.15 service factor, you can run that over a 4-to-1 speed range with a constant torque load like a conveyor. You can run it over a 10-to-1 speed range with a variable torque load. Now, the full load amps remains the same unless the manufacturer tells you differently. And in this case, the manufacturer says the full load amps without a VFD is 229, and the full load amps with a VFD is 239. So what that's saying is that this motor is conservatively designed enough such that they can give you a little bit of your service factor back. They're going to take most of that 1.15 service factor, but they're going to give you just a little bit back and actually allow you to run at 239 amps at full load on a variable frequency drives. Again, most nameplates on motors do not have this inverter duty section on the nameplate. And so if it doesn't have this section on the nameplate, you're going to say that the full load amps is the same, whether it is running on a VFD or not. Now here's another VFD or motor nameplate. Notice up here it says on inverter duty, it can run over a 10-to-1 speed range variable torque or a 4-to-1 speed range constant torque. So you get different things on different nameplates, and clearly when you look at this, it's obviously an inverter duty motor. Now it doesn't say NEMA MG1 Part 31. That would be nice if it did, but again, different manufacturers put different things on the nameplate. The last nameplate didn't have the speed range that this one does. Here's another nameplate. This is from Marathon, and if you look on the bottom there where I have outlined in red, it says PWM VFD, so obviously they intend for you to be able to run this motor on a variable frequency drive. And this says your 10-to-1 variable torque, but only a 2-to-1 constant torque. So here you can only run half. That's very important to know what that is. And again, they show you it's only a 1.0 service factor when you're running on a variable frequency drive. But, and it's under the red, so you can't see it very well. But across the line, the service factor is 1.15. On a PWM VFD, it is 1.0. Now, this is right out of your booklet. For an adjustable speed drive or variable frequency drive application, you should use an inverter duty motor. We've talked a little bit about what an inverter duty motor is. There should be something on the nameplate or in the cut sheet that says that that motor is going to run on a PWM drive, and it should meet NEMA MG1 Part 31. Next, use supply conductors designed for variable frequency drive circuits. They call them adjustable speed drives. Now, we will get into this in a moment. Most people do not do that, but we will talk about that. And finally, use your shaft grounding system. So ESA says anytime you have a motor on a drive, you should have these three things: inverter duty motor with a shaft grounding system or insulated bearings, and use ASD supply conductors. Okay, let's talk about DVDT first. This is from a website. I'm spacing it now, but this is a manufacturer of DVDT filters, and there are two things that can happen. You can have reflective wave phenomena or resonant circuit phenomena. Rather than go through the details of that, we're going to just show you what it looks like. I like pictures. All right, now I've talked a lot about MG1, and you're saying, what is that? Well, NEMA, that's the National Electrical Manufacturers Association, has a standard for motors. Their standard for motors is MG1, and Part 30 of MG1 is for all motors. Part 31 of MG1 is for variable frequency rated motors. Now you'll notice that all motors should have 1 kV insulation. That insulation is, there are several insulation levels. For instance, you know that a motor by NEMA standards is rated for twice line-to-line voltage plus 1,000 volts. That's a rating for surges. This is a rating for outputs of variable frequency drives. And the insulation is rated for 1 kV and a rise time of 2 microseconds. If you get a VFD rated motor, it has premium insulation in it. We call that in the industry high spike wire. And the high spike wire, it has to be rated for 3.1 times the rated voltage of the motor, and it's good for a 0.1 microsecond rise time. Now, generally, we just look at the voltage. So this is 1 kV, and for a 480 volt motor, I'm going to call this 1600 volts because most high spike wire is rated for 1600 volts, although 3.1 times V rated is a little bit less than that. So I'm giving you the actual wording in the standard. Again, this is the Emerson nameplate, and I'm reminding you here, it says NEMA MG1 Part 31. That means it has the premium insulation for use with a variable frequency drive. In NEMA, this is how you measure the rise time. That's in your, that will be in the slide here. I'm not going to talk about that in detail. And this is your common mode voltage that has to do with bearings. So we're going to get into that in a moment. I want to look at this. Now, this is off of, again, a website of a manufacturer of DVDT filters. DVDT, of course, stands for differential of voltage with respect to time, or derivative of voltage with respect to time. All it really means is it reduces the rise time. DVDT means how fast is the voltage changing. So look at here, and here's one particular motor with one particular drive, and it's got 70 feet of cable between the motor and the drive. Notice that the red line is at 1000 volts, and the top of the graph is 1600 volts. That's really nice because the 1000 volts is your standard motor, NEMA MG1 Part 30. The top of the graph is your VFD rated motor, NEMA MG1 Part 31. Now you get all these little spikes coming out of the VFD, and you will notice over here that some of those spikes are barely going above 1000 volts. So if you had a standard motor, in theory, this could cause premature motor insulation. Now over here we have 500 feet of cable, and the longer cable allows for higher spikes, and you can see those spikes are getting increasingly over 1000 volts. You certainly wouldn't want to use this on a standard motor on a situation like this. Now notice the carrier frequency is 2.5 kilohertz. That's the frequency of the pulses. If we change that carrier frequency to 8 kilohertz, things get much worse. So I think you can see why we want to use a motor with the high spike wire that meets NEMA MG1 Part 31 anytime we're going to put a motor on a variable frequency drive. Now, is there another way? I'm mentioning a supplier here. This is a supplier, probably our favored supplier, Mitsubishi. They have something called soft PWM. And the rule of thumb is that anytime you have a motor, even if it's a high spike wire, VFD rated motor, if the cable is more than 100 feet between the motor and the drive, you should apply a DVDT filter. And what that will do, of course, is to reduce those spikes. And it will reduce those spikes to below 1000 volts. There are some drives, Mitsubishi is not the only one, but sometimes it's hard to find this information, who have proprietary solutions. This is Mitsubishi's, they call it soft PWM. And if you have a VFD rated motor, NEMA MG1 Part 31 with high spike wire, you can go up to 500 meters for 3 horsepower and above without requiring a DVDT filter. They also, instead of just having a standard frequency, they vary that frequency. You can see in the test here, this is a 4 kilohertz frequency. This is soft PWM, where they vary the frequency between 2 and 6 kilohertz, and that prevents most of those reflected waves and the resonances from occurring. Again, this is a patented way of doing things, but we've tested it, does a marvelous job. The other thing is because of magnetostriction, whenever you look at, or whenever you listen to a motor on a VFD, you notice that they sing. They have that little noise that you don't hear across the line. Well, that's the carrier frequency. And if you change the carrier frequency, which you can do on any variable frequency drive, then you will hear that frequency change. With soft PWM, this is without soft PWM on the left, and with soft PWM on the right, you will notice that that noise mostly goes away, and you get a much more complex, pleasing noise rather than that really irritating sine wave kind of noise. So it's another advantage of soft PWM. So this is a little bit of a summary here. DVDT filters reduce voltage spikes below 1,000 volts. They slow down the PWM DVDT by a factor of 3. They reduce your common mode currents, which we'll talk about in a moment, by approximately 30%. And they protect both the motor and the cable insulation. So you can consider using that whenever your cable length exceeds 100 feet. Different manufacturers have different numbers for that. It just depends on how conservative they want to be. 100 feet is what I've chosen. Some manufacturers will say 70 feet, or some will go 125 feet. But I think 100 feet is not a bad rule of thumb. Now, the other thing you can do is you can not put in a DVDT filter. You can run the motor in the drive, and you can go out with your oscilloscope and measure those voltages. And if you don't see any voltages over 1,000 volts, then you don't need a DVDT filter. If you do see them over 1,000 volts, then you could go back, if you leave room in your VFD cabinet, and add a DVDT filter. You also want to stay within the manufacturer's recommendations for carrier frequency. We could talk a lot about carrier frequency, and we will, but not today. That'll be in our VFD class. A little hint: if your motor runs fine on sine wave power but trips on a VFD, then you should have that motor surge tested with a Baker surge tester by a qualified motor rewind shop, because your motor insulation is on the verge of failure probably, and the VFD is seeing that because it's so sensitive, but just your across the line starter doesn't see that. But you certainly want to address that. Now let's take a look at VFD cable selection. Why would you need a special cable for VFDs? Well, one of the things is VFDs that carrier frequency is 2, 3, 4, 5 kilohertz, and that causes noise that can actually propagate through the air. So if you have walkie-talkies, radios, sometimes you turn on the motor and you get noise. Also, this noise can propagate by a capacitance to other wires that might be in the same conduit. That's why we should never, ever run your emergency stop or your thermal measurements or anything in the same conduit with the VFD, because the VFD power wires, because you will get noise induced in those wires. In any case, let's take a look here. Now, they recommend, if you really want the Cadillac, that you build your cable like this. First of all, you don't use 3 wires. You don't use 3 separate wires. You use one cable that has the 3 wires in it. So you can see the first thing we do is we take the UVW or the L1, L2, L3, whatever, and they are in a triangle pattern. What that does is keep the capacitance between any 2 of the phases the same, and that will keep you more balanced. The second thing you do is you use 3-phase symmetrical grounds. Most cable have a ground conductor, but if you use these VFD rated cables, they actually have 3 ground conductors, at least most of them. And so here's a ground, here's a ground, here's a ground. Why? Again, you want to keep the capacitance between each of those phases and ground the same. So you're going to have 3 symmetrical grounds. And then finally, you're going to have an overall shield, which protects, which tries to keep the noise inside and keep the capacitive currents inside. So these are great cables. ESA recommends you use one on every VFD application. I must tell you that most people don't do that. However, more and more people are beginning to use VFD rated cable. This is only from the VFD to the motor. It is not the cable feeding the VFD. There's no reason to use this on the cable feeding the VFD, only between the VFD and the motor. More people are using this. As more people use it, the price comes down, but there will always be a premium price. I particularly kind of favor this. If I was designing a system, I would add this kind of cable. Here's a nice picture of the end of a cable, and this shows you kind of the same thing, how the shields work. This is a recommendation. This is from T-Mike, Toshiba Mitsubishi Electrical Industrial Corporation, manufacturer of mostly medium voltage drives, and it will tell you whether certain types of cable are recommended or not recommended. And I'm not going through all that. You can look at it in your presentation when you download it if you are interested. Now, VFDs and motor bearings. This is very interesting. When Tesla designed the three-phase power system, he used sine waves. And when you have sine waves, then interestingly, if you add together A phase, B phase, and C phase at any moment in time, they always equal 0. And that, in theory, results in 0 common mode voltage. Common mode voltage is generally a voltage that will appear between the frame of your motor and the shaft of your motor. When you put a VFD on it, it doesn't work that way. No VFD works that way. So when you put the VFD on there, you end up with common mode voltages. In other words, voltages between the shaft of the motor and the frame of the motor. Well, what is between the shaft of the motor and the frame of the motor? The bearings. So as the voltage increases, it gets to a certain point where it will arc through the oil film in that bearing. And when it does that, it goes from the inner race through the film, through the ball, through another of the film on the other side, and then the outer race. And it's like welding on your ball bearings. So not good. This is a picture of the common mode voltages when we're measuring them between the frame and the shaft of the motor. And this is a close-up of that. You can see that the voltage increases, and all of a sudden, right here, it arcs across, and so you can see the voltage drop suddenly because it has discharged through the bearing. This is bearing pitting damage. So if you look at it under an electron microscope, then you will see this pitting occurring in the lower right. Obviously, we don't want to see that in our bearings. If you're looking at it with your naked eye, you can't see that. What you will see is bearing pitting damage. So you will see something, but it looks more like a matting or a less glossy finish on your bearings. Your bearings should always look shiny and glossy, and if you see this matted finish, then that is bearing pitting damage from a variable frequency drive. And if you magnify that, you can see it's composed of all these pits. That is going to cause premature bearing failure. As it gets worse, it turns into bearing fluting damage. So you can see over here, this looks like the fluting. You've seen fluted columns on like Greek temples and a lot of architecture. That's where they get that name from. And once it gets here, your bearing is just going to sing. It's going to get really loud. You're going to see the vibration pick up, and you are then on the verge of a bearing failure. Here is the inner race and the outer race. Whenever you get a VFD that's run, a motor that's run on a VFD, and you take it to a motor shop for repair, they should always cut the bearing. Make sure that they do that. Cut the bearing, wipe the grease out, and inspect for damage here. How do you fix that? Well, I'm just going to cover two methods. One is a DVDT filter or a sine wave filter, and as you can see, that reduces the common mode voltage. I don't know of anybody who uses that technique because there are better techniques available, but it does help. Over here is my favorite. That's called an insulated bearing. Now, the insulated bearing actually has, and this is a full ceramic bearing, the balls are made out of ceramic. I mean, that's incredible. They do have insulated bearings like this where they use a standard bearing and just put an insulated coating over the outside of the bearing to insulate it from the shaft. This in theory works. We have not been totally happy with that way of doing things. And so we really prefer the insulated bearings here. Um, the insulated bearings, it's not in there, will last 10 times as long as a standard bearing. They're very light. The bearing will run cooler because they slip better. They have less viscosity in there. You can use the same type of grease on them, and they're pretty great. So why doesn't everybody use insulated bearings? Cost. An insulated bearing depends on the motor, but we'll just say it's maybe 4 times the cost of a standard bearing, but it's a great way to go. There's another way to go, and that is by using what we call shaft grounding rings. These are the little carbon fibers that you see on your printer that take the static electricity off of there. And these are some of the things that does. I'm going to go to pictures because I think they make more sense. Here's a shaft grounding ring, and you can see the outside of the ring is attached to the motor frame. And then there are little tiny carbon fibers in here that actually touch the motor shaft, and they basically just short the shaft to the frame. So you still get the currents, but the currents, instead of going through the bearings, go through this grounding ring, and that prevents the voltage from getting high enough so that it can arc through the bearing. Do these work? Well, I was kind of skeptical when they first came out. I can assure you they work. And we have had very good luck with them. We put shaft grounding rings on lots of motors these days. And these are different ways of buying grounding rings and mounting them. It's good to have someone who is a pretty much qualified motor guy to mount the rings for you. You can even glue them on, as I'm showing you here. It's also nice to have a colloidal silver shaft coating around the shaft in order to give that a lower resistance, make it really smooth. According to according to the bearing current manufacturers, that's the people that manufacture these grounding rings. If you have a motor under about 100 horsepower, you just need 1 grounding ring. And if you have a motor over 100 horsepower, come on, there we go, over 100 horsepower, they recommend here that you have a grounding ring here on the side of the driven equipment, and an insulated bearing on the other side, because on large motors, you can get circulating currents within the motor that will destroy your bearing. So that's straight from Aegis, the people who have the patent on this technology. Okay, startup procedures. We only have about 5 minutes left, so I'm not going to go through these in detail, except to say, guess where you can find startup procedures? That's right, in the booklet that we'll give you electronically, and you can simply request one, and we will send you a printed booklet. So this tells you startup procedures for a motor. Here's some testing. That's an IR test. It tells you what your minimum test voltage is, minimum insulation should be on a motor. There's your motor nameplate again. This is motor baseline. I'm not going to cover this much because you may or may not have that booklet in front of you, but on page 22 of that booklet, it gives you all of the things that you should write down anytime you start a motor. And we're not talking about a 1/2 horsepower motor here probably, but a large motor, you should do tests on it and you should write down all those things. If you don't do that, how are you going to know if you do testing in the future, how it compared with what it looked like when that motor was new? Operational monitoring and maintenance. On page 13 of the book, it tells you different ways of doing maintenance. Of course, a lot of people use what's called run-to-fail maintenance. You fix it when it fails. There are more sophisticated methods of maintenance. Your preventative maintenance, your predictive maintenance, and your reliability-based maintenance. And we could spend a whole seminar just talking about that. Infrared cameras are a really great tool for detecting temperature, and I think we've talked about using some of the places that you can use infrared cameras. FLIR makes a great infrared camera. Fluke makes some very good cameras too. Here's some vibration analysis telling you what is acceptable in terms of vibration. You can find that in your book. This is a shock pulse method. There is a company that makes shock pulse monitors. They actually look at vibrations in your bearings and analyze them with a computer in order to tell whether that bearing is getting worse or whether it's near failure. And you can buy this little one for about $2,000. You just go push that thing on your bearing, do it 3 times on 3 different places on the bearing, and it will give you a red, green, or blue light to tell you your bearing's good, green. Did I say blue? Red, yellow, or green. Green means your bearing's good. Red means your bearing's bad. You should shut down the motor immediately. And yellow would mean that you've got a bearing that is compromised, and so you should plan for taking that out of service. Then there are shock pulse monitors that are more expensive than that, and some are meant to be put on the bearing full-time for full-time monitoring, which is something worth doing if you have a really large, really critical motor. Here's an IR test, the insulation resistance test. This you can find in your booklet. It tells you all about that. Here's your dielectric absorption ratio test. And again, it tells you what's acceptable, what's not, and that's all described in your book. Winding resistance measurements, winding inductance, and capacitor measurements. This is a fancy one called the motor current signature analysis, a device that looks at the motor current and evaluates the signature and determines whether the motor is having problems. This is not just for bearings, this is for the whole motor. This is an example of an MCA test. Doesn't look very obvious there, but if you have an MCA tester, then that's pretty fancy stuff that we're able to do these days. There's a high pot test, talks about how to do that. These are some motors out of our shop. One of the things you want to do is try to keep a motor clean. And up on the upper left, you can see this is abrasion. That's an open motor in which you've had abrasive material flowing through the motor to cool it. And here's wasp's nests, not uncommon. You can see these fins on the outside of a totally enclosed fan-cooled motor. Really, we need to keep that stuff cool. If those fins get blocked up, then the motor's going to run hot because they need that in order to cool themselves. If your motor is running too hot, here's a little checklist you can go through and ask yourself all these questions to see if one of those things is causing your motor to run too hot. And here's some motors that have run too hot. Here's one that I talked about a minute ago. The cooling fins are filled with debris. That motor is going to run too hot. So make sure you keep that motor cool. Voltage unbalance, 3.5% voltage unbalance can cause 25% additional motor heating. So that's certainly something that can cause a hotter running motor. And here's some graphs that show you voltage unbalance. Recommended motor protection for under 1,000 volts. This is typical. You get solid state relays. If you want something more sophisticated, then that's your better. And if you want to get very sophisticated, then there's your best. This is also zero sequence monitoring, which is recommended for all medium voltage motors. And a very great way to detect motor installation failure early while the cost to rewind it is cheap because you haven't done a lot of damage. There's differential protection, and over 1,000 volts, there's your good protection, your better protection, and your best protection. And we've recommended all the things that you should have to protect your motor, and that will be in your slide pool. Motor space heaters, good when you think that there might be condensation within the motor. Then motor storage, anytime you put it into a motor storage, you must go through procedures for that. And guess where you can find those procedures? In your booklet. This is a brand new motor that was stored and it wasn't rotated, and those are the marks left by the ball bearings because of vibration. There was a train running by that motor storage facility. So motors need to be stored properly, and on page 30, it will tell you all the information you need to know about how properly storing a motor. And when you're going to remove it from storage and put it back into service on page 7, it gives you all the procedures for doing that. Repair or replace, your motor shop can tell you that. Typically, we look at 50 horsepower, but it depends on the size. This is your life cycle costs, all of which is in the book. And I'm sorry I'm going through this kind of quickly. Make sure you use a quality motor repair facility, and these are the things you want to check with your motor repair facility. These are certifications. So ESA, Green Motors, UL, and bearing certification facilities. If you, that's one of the things I would look at in determining the quality of a motor facility. is the amount of training they've gone through and the certifications. ESA, you can be a member of ESA, but they also have a full accreditation. All of our shops are ESA accredited, and we also have the Green Motors, the UL, and the two different bearing suppliers in which we're certified. And there's a picture. So we are at the end. Went a couple of minutes over. I apologize. And in the amount of time we have, we just don't have time to go through all of these things. But again, I would encourage you to get this book, and you can go back through the slides if you want to study any of those particular subjects in more detail. So Tyler, I will turn it back to you.
Great. Our first question we had come in: is there a problem mixing different types or manufacturers of lubricant?
Yeah, that's a very good question. There is certainly a problem mixing different types. Different manufacturers, in theory, if you have, let's say, a polyurea grease, and you want to switch from Chevron to Shell or from Shell to Exxon, you should be fine. I don't think it's a bad idea to standardize on one particular manufacturer, but in theory, there should be no problem. But of course, if the grease is a different type, that's a huge problem.
Okay. Why is the cable less important for medium voltage motors versus low voltage motors for VFD applications?
Oh, now that is a wonderful question. And the answer is the output waveform. Now, on a low voltage motor, the DC bus is about 650 volts, we'll say, on a 480 volt VFD. And so those pulses, the PWM pulses going to the motor, they're going from 0 to 650 volts, then back to 0. And then 0 to negative 650 volts and back to 0. And so it's a terrible motor waveform. I mean, I wish we had something better. Now, with medium voltages, it depends on the drive. And so let me just mention that some drives are terrible. Some drives have terrible outputs. We would recommend, and I think my company would recommend, but I recommend a minimum of a 5-step output. So, or a 5-level output. So what does that mean? That means that you don't just go on and off. You turn it on, let's say 25% voltage, then you add another 25% voltage, then you add another 25% voltage, then you add another 25% voltage. So it looks kind of like stairs. And so you're not going from 0 to full voltage suddenly. You are gradually going up, and it looks like a sine wave kind of, because as you're putting in these steps are gradually increasing as you get towards the peak of your sine wave, and then down. The drive that is my favorite right now that we sell has a 9-level output. So that means there are 9 levels in the output, and it's basically a sine wave. I mean, if you look at it, it's got a little bit of ripple in, but it's almost a perfect sine wave. So again, depends on the drive, but when you have a perfect sine wave coming out of that drive, it's almost like an across the line motor. And you can get that kind of technology in medium voltage. That kind of technology is not available in low voltage. And again, medium voltage is over 1,000 volts, low voltage is up to 1,000 volts.
For a motor over 100 horsepower, does it matter where the grounding ring and insulated bearings are, where they're installed, as long as they are opposite of each other?
Yeah, that's a good question. Let me go back on the last question I just mentioned. We have done a medium voltage seminar, and that's available on our YouTube channel, I believe. Tyler, can you tell me how they would get to that medium voltage seminar?
Yeah, all of our seminars and webinars are hosted at emcsolutions.com/webinars. I'll send out the link in the chat.
All right, so I tried to describe the steps on a medium voltage motor, but really you need to see them. If you actually see them, it makes a lot more sense. And so if you go to our medium voltage webinar, you will see that, and then you'll say, oh, now I understand what he's saying. Now, in terms of the bearings, this can get quite complicated. You have 2 bearings on a motor, but there's also a third bearing. And the third bearing is in your load, in your fan or in your pump or whatever. And so whether you have a conductive or a non-conductive coupling makes a big difference. Maybe I should say an insulated coupling. And so all I'm going to say is if you have an insulated bearing on one side and a shaft grounding ring on the other side, the safest way to do that is to put that shaft grounding ring where the shaft goes out to the load. However, depending upon the coupling and so on, it may not make a difference. Good thing to do is find out what kind of coupling you have, and then you can certainly talk to the people in our motor shop who are experts at this and who go through the Aegis training and see for your particular application where it is. But if it's convenient, we'd recommend the shaft grounding ring on the side that connects to the load.
Can you change the fan on a motor that you know will be running under max RPM?
So I guess what they're saying is, can you change the fan on the motor in order to cause it to get better cooling? In other words, maybe could you put a bigger fan on that motor and get more cooling at lower speeds? Well, most fans, if you look at them on small motors, they're not very sophisticated. They just have straight blades, and the blade can only be so long, because if you make it longer, it's not going to fit on the motor. It's going to rub on the end bell there. So I would say, in theory, you can do this. And on larger motors, you definitely could go to the motor manufacturer and ask if he could provide a fan that will pump more air at lower speeds. However, I will say that on smaller motors, as a matter of practicality, typically the answer is no. There just aren't fans available that will pump more air at lower speeds.
Great. That looks like it's all of our questions. So we want to thank you for joining us today, and we look forward to seeing you on the next webinar.